Hey guys, good morning. Um, so this video is for your final exam for your second semester of chemistry. Um, what I have really seen in all my classes across the board is that a lot of you still struggle with the math and not knowing how to set it up. You can do math, plugging it in the calculator, but making sure you put the correct items in the correct charts, basically. So a lot of this video is going to be review, going over the study guide that was passed out, but also really focusing on the math portion and explaining that. So concept parts, any of the definitions, we're just going to breeze through really fast. Again, my classes. If you are watching this and you have a question, please remind message me. I got my phone. I'll see it come up. So I got my coffee, got the study guide, and we're going to be going through it. So here we go. All right, so in all my classes, we were able to cover the study guide in whole. Students that have OSS, ISS right now, a lot of this is for you to make sure as well that you have the correct information before we start. So your test is literally broken down to the 7 different units that we had this past semester. It's going to start with moles, then move on to stoichiometry, then solutions, and so forth. So here we go. Please remember that when we're talking about a mole, we are literally talking about a quantity. There's no set size to moles. There's no set grams to moles. There are always set numbers, meaning that whenever I have a mole of anything in this whole wide world, if it's a mole of coffee, if it is a mole of H2O, a mole of eggs, I'm saying that I have 6.02 times 10 to the 23rd power of those items. So remember that when you're talking from particles, that the words atoms, molecules, ions, formula unit, and electrons can be able to describe when it's talking about a particle. So in number 2 here, it's asking you, it gives you 9.03 times 10 to the 23rd powers of molecules of MgNO3 parentheses 2. So what we do is set up a t-chart. We are able to put our given always, always, always in the left top box. You always start with what they give you. And because they're just asking you to go from a molecules to a mole, you just put 6.02 times 10 to the 23rd power of molecules, Avogadro's number, on the bottom to make 1 mole. And when you divide by that, you get 1.5 moles of magnesium NO3 2. Then, on the third one, they're asking you to go from moles to grams. And remember that every single element has its own AMU, atomic mass unit. And you can find that on the periodic table. So, all you do, you start with your given. And your given in this case is going to be 8.3 times 10 to the 23rd molecules of sodium chloride, NaCl. And because we're going from molecules to moles, simply put 6.02 times 10 to the 23rd molecules on the bottom to make 1 mole. And because every element has its own AMU, you have to find the AMU for the grams for sodium chloride. So when you add up sodium chloride and chlorine together, you get 58.44 grams for every 1 mole. So when you multiply across, divide by the bottom, you get 80.57 grams of sodium chloride. All right, so on number 4, 1 mole of pure substance, any pure substance, if it's just hydrogen, if it's just H2O, if it is sodium chloride, salt, whatever that is, it is always going to be 6.02 times 10 to the 23rd of those atoms. And this is called Avogadro's number. All right, number 5 here. What they're asking you is the percent composition. So imagine 3 friends get on an elevator. All the friends weigh a different weight. And you want to figure out what your percent of that overall weight is. So for A here, you have Fe3O4. So first, you have to figure out the overall molar mass of that compound. So I have 3 Fe's, so I times it by 55.85, and I get 167.55. Then I have to do it for oxygen. So 4 times 16, which again, 55.85 and 16, I just found them on the periodic table. Just look at your periodic table and you're able to get those numbers. So 4 times 16 is 64. I add them all together, and that's 231.55 grams. Now, that's not my answer. We're trying to find a percent of that being for Fe. So, because Fe altogether has 167.55 grams, you divide it by the overall of 231.55, and you get a decimal of 0.723. And remember that when you want to get it into percent, you just scooch your decimal over twice, and that will give you 72.3%. All right, for B, so this one's a little more complicated because the subscript on the outside is on the parentheses. So we do have 2 aluminum, and we have, in this case, 3 sulfur. Because S is on the inside of the parentheses, the 3 will multiply by 1, which gives you 3. Then for oxygen, because you have a 4 and a 3, that means you're going to times them. 4 times 3 is 12. So you take the AMUs from the periodic table. Again, look at your periodic table. For aluminum, that's 26.98. For sulfur, that's 32.07. And for oxygen, that's 16. When you multiply them by the quantity that you have, you end up with the individual molar mass. You add them all together, and you get the entire compound's molar mass of 342.17. So, because I just want sulfur, I take 96.21, divide it by the 342.17. Again, that gives me a decimal of 0.2812. I scooch my decimal over twice, and I get the percent of 28.12%. All right. Sorry guys, I'm still trying to get over being sick. For 6, this is identifying empirical. Remember, there's a difference between empirical and molecular formulas. Empirical is literally the smallest it could go. When you're looking for empirical, you want to look for odd numbers or prime numbers that won't get smaller unless it gets into a decimal, which that right now can't happen. So for A, because carbon has a 3, that's the smallest C3H6O2 can get. But here, your carbon has a 6, your hydrogen has 12, and your oxygen has 4. Those can each be divided by 2 to get to be smaller. So thus, the first one, C3H6O2, is my smallest. For B, that's going to be CH3. For C here, that's going to be C11, because that's odd number, it's prime as well. H12O6. For D, NO3 for your choices. with number 6 here, this problem 6, you're simply looking for the one that cannot be made to be smaller. It's the simplest format. Moleculars are the ones that are bigger, the ones that represent true molecules. Sugar compounds can be broken into smaller empiricals, but their true formula is much larger, and different sugars have different compounds. So, 7. I know it looks scary to try to find the empirical formula when you're given percents, but it's not that scary, and just take it step by step. So first, you're given percents for each of your given elements. Carbon had 60%, hydrogen had a 4.44%, and oxygen had a 35.56%. So I simply just make those into grams. And so 60%, 60, 4.44, 4.44, 35.56, 35.6. And on your second step for my classes, first step was to transfer it over. Second step, divide by the AMU. Look at your periodic table. You're going to see that carbon has a 12.01. So 60 divide by 12.01 gives you 4.996. Don't worry about the 2 yet. Just focus on what you get. Then for hydrogen, you have a 4.44. Divide by 1.01. Again, I got that 1.01 from the periodic table, the AMU. Then you take that 35.56 and divide it by 16. So I end up with 4.996, 4.396, and a 2.22. Now, none of those are whole numbers, and we want to get these to be whole numbers so we can build our empirical formula, our empirical compound. So I take the smallest one, and when I compare the 4.996, the 4.396, and the 2.22, the smallest of those 3 numbers is the 2.22. So I divide each of these. What you do to one, you gotta do to the other. So I divide each of them by 2.222. Now that gets me closer to whole numbers. That gives me a 2.25, a 1.97, which is really close to 2, and a 1. Now, the 1.97 is so close that he can just be 2. But the 2.25, you can't round him up to 3, and you can't round him down to 2. He's like in that awkward stage. So, in this case, think of it this way. If you have a 0.25, that's like having 4 quarters in a dollar. If you put this in a money sense, like in a relationship of something like we see every day, that is going to be a lot easier. So if I had a 0.33, I would times it by 3. If I had a 0.20, I would times it by 5. But in this case, we have a 2.25. So that means that's going to be like 4 quarters in a dollar. So again, what I do to one, I do to the rest. So 4, you multiply each by 4. 2.25 times 4 is 9. And 1.97 times 4 is close enough for it to be 8. Then 1 times 4 is 4. So you just build your empirical formula in the order that it went. So carbon, hydrogen, oxygen. So carbon, 9. Hydrogen, 8. Oxygen, 4. That is my empirical formula for this given percents. Now, next one is 8. So in this one, they tell you your empirical formula. And you're starting with empirical, but they tell you, hey, I have a compound that I want you to find that's a molecular, but here's the given molar mass of it. So the first thing we do, because they didn't give us the empirical molar mass, we need to find the empirical molar mass, which you're given C5H4. So again, look at your periodic table. I take C5H4, times them by the AMUs, and I get a total of 64.09. That's the empirical molecular formula, molecular mass, so molar mass. So I take the given molar mass of my molecular formula, which is 128.16, and I divide him by the empirical molar mass, which is 64.09, which gives me close enough number of 2. So what you do is just simply multiply. You don't have 2 in front of C5H4, but you multiply the subscripts. So C5 times 2 is C10. H4 times 2 is H8. This C10H8 is going to be your molecular formula. We went from an empirical to a molecular. All right, that is for moles. For the whole unit, that is what you need to know for your test. I would definitely focus on each of these math problems. I would focus on understanding and remembering 6.02 times 10 to the 23rd for Avogadro's number. Now, let's go over stoichiometry. And I get that balancing equations is no one's favorite. I get that right now. And there's multiple ways that this has been shown and taught. And so I want you to find the best way for you. And some of the classes you've seen the rap sheet, RAP, reaction products, the atoms that you have. Then you've also seen someone go straight down the line and put them and balance them back and forth. Or you've also seen the different colors with the different dots. Either way, figure out what is best for you. I know on my YouTube video, there is already a physical demonstration working with a virtual lab showing you the balancing of those. So again, if you are struggling with balancing equations, please go work those and practice with those. Go to the website that I put the link with and make sure that you can do that. All right, so for the given balance equation, please remember that the coefficients in front represents the moles. The subscripts at the side right here, like CH4, means that there would be 4 hydrogen within 1 mole. And right now I have 2. So it would have a ratio. My ratio here would be 2, 1, 2, 4 for this given compound, for this given equation. So it's balanced. Now I can focus on working out each of these different problems. Please remember there's 3 different types that you're going to be seeing. You're going to have a mole to mole, which is the first one demonstrated here. Then for 11, this is going to be moles to grams. And then your last is grams to grams. And each of those, you can do the bridge, the T-charts. So we're going to go over each of those. All right, for the first one, 10. You start with 1.5 moles of S8. Now, because that's your given, he automatically goes there. The first bridge that you're building is a mole ratio. You don't have to find the grams. We're just finding the moles of something else. So we start with a 1.5 moles of S8. And because moles of S8 are on top, the unit right there is on top, he goes on bottom. I know a lot of you struggle, oh, Ms. D, which one goes on top, which one goes on bottom? Hint, hint, wink, wink, love Ms. D. If you're given here, starts with moles S8, moles of S8 go on bottom. Then, because we're just going from moles to moles, I look and I see, oh, I'm trying to get to become CS2. So I put the unit moles CS2, and I look up here at my balance equation, and I see that in front of S8 I have a 1, and in front of CS2 I have a 2. So it's a 1 to 2 ratio. So I take my 1.5 times them by 2, and you can divide by 1, but it's going to be the same answer. And I end up with 3 moles of CS2. Then we move on to a moles to grams. Now, whenever you cannot, like, period, jump from one type of substance, so the moles of CS2 to the grams of something else. Whenever you're switching between one compound in a balance equation to another, you have to have your mole ratio. You have to be able to convert it first. So that's what we're going to do. So we start with moles, 8 moles of CS2. And that's not the grams I'm trying to find. I'm trying to find the grams of CH4. So I first have to take it from the moles of CS2 to the moles of CH4. So this first part right here is a mole ratio. And I simply looked at my balance equation and I saw that I had 2 moles of CS2. And I also had 2 moles, because of the coefficient in front, 2 moles of CH4. So there, I was able to build and get him into a moles of CH4. Now, again, because on top here is a moles of CH4, what I'm going to put in the bottom down here are the moles of CH4. And because I'm a smart, brilliant chemistry kid, I know that 1 mole of any substance in the whole entire world will equal the grams that I can find on my periodic table. So automatically I just put 1 mole of CH4 to grams, and I look at my periodic table and I add up the carbon of 12.01 and I add in 4.04 for the hydrogen, and it gives me 16.05 grams of CH4. So I multiply across, divide by the bottom, and when I do that, I get 128.4 grams of CH4. All right, 12. These are the harder ones. This is where people stumble a lot. Again, please remember, you cannot simply jump from a grams of one type of compound automatically to something else. You have to be able to get it into moles first, to do a mole to mole ratio. So the first thing I do, I have 50 grams of CS2. That's my starter. So he goes in top right here. And I look at my periodic table and I discover from my AMUs that I have 76.5 grams of CS2 for every 1 mole. Again, pure substance, the grams of pure substance will equal 1 mole always. So 76.5 grams CS2 goes on the bottom, 1 mole of CS2 go on top. Then I discover that I want to do a mole ratio. So I look at my balance equation and I see that CS2 has a 2 coefficient and my CH4 has a 2 coefficient. So it's a 2 to 2 ratio. Now, moles of CH4 is not what I want. The grams are. So again, I'm a smart, brilliant chemistry baby. So thus, I know that 1 mole of CH4, my pure substance, will equal the number I find on the periodic table. So when I add up all the AMUs for the CH4, I get 16.05 CH4. And when I multiply across, and I also need to multiply the bottom before I divide. So I multiply across, divide by the bottoms, I get 10.54 grams of CH4. Now, number 13 is just asking you for the molar ratio, the mole ratio. So it's asking for CH4 and H2S. So I look up here. CH4 has a 2. H2S has a 4. So he has a 2 to 4 ratio, which I could make smaller to a 1 to 2 ratio. All right, number 14. So we have a law of conservation. Nothing can be created nor destroyed, and as Ms. D says, just reorganized. So thus, the law of conservation of mass states that the number of reactants, the grams of reactants that I begin with, must equal the grams of the products. So thus, the mass of the reactants must equal the mass of your products. If I start off with 125 grams of reactants on one side, that means automatically for your products, you will have 125 grams amongst the compounds. They don't disappear. They don't magically go poof. We do not live in a Harry Potter world. So they are still there. They may be in different forms, but the total grams, your total mass that you start with and you end with are still there in some form. All right, so solutions. This part is a little easier for some of you guys, so we're just going to breeze through the definitions. 15 was B, 16 was C, 17 was D, 18 was F, 19 was E, 20 was A. Love Miss D, you need to memorize your definitions if you have not done so. All right, for this one, I'm going to open this a little bigger. All right. So for 21, a solution with 30 grams of sodium chloride in 100 grams of water at 60 degrees Celsius. Now, guys, please know and recognize that this whole thing, this whole solubility graph right here is grams of water right here as your solute. Grams of solute divided by 100 grams of water, so that's solvent. All right, so temperature is at the bottom. Grams of your solute. In this case, my solute is going to be sodium chloride, which is salt. And I have 30 grams of him. So I'm going to go to the 30 mark right here. And they're saying that it's going to be at 60 degrees Celsius. So you just simply find the intersect, the x and y of it. Think of it that way. X and y, so 60, 30. Now, you're trying to compare him and see if he's saturated, unsaturated, supersaturated. And I don't know if it's easy to see, but right here is my purple line for sodium chloride. And I put a dot here. So because he is below the line, that is unsaturated. Now, hypothetically, if he was on the line, straight on the line, he would be saturated. If anywhere above the line here, that would be supersaturated. So for 21, with that position on the graph, it would be unsaturated. 22 is asking you for a temperature. They're asking you to find something saturated. So again, sorry guys, it's 50 grams of KCl. So 50 grams here, and I find where it intersects my KCl line. My KCl line is here. It's a curve. And I'm at my 50 mark, and I go straight across the 50 until I see that he intersects with KCl. And KCl intersect with him to be saturated at the 80 degrees Celsius. So thus, for 22, it's going to be 80 degrees Celsius. Then, for 23, how many grams of KClO3 is dissolved at 100 grams of water at 90 degrees Celsius? So, again, I look for my KCl line right here. KClO3. KClO3. And at this time, I'm not starting with my grams, I'm starting with a temperature. And don't let the 100 grams of water trip you guys up. That's just saying it's this graph. That is it. So you're on the right graph. All right, so you're at 90 degrees Celsius, and you just go straight up till you find the point in which KClO3's line intersects, which happened to be at 50 grams. So I have another mark right there. So I just write 50 grams. 24 is asking you to see that when you have gases trying to be dissolved into a liquid, you have to decrease the temperature in order to get them to dissolve. So please notice that as the temperature increased, NH3, which is a gas, decreased its solubility because the temperature increased. Remember that gases are unique, that when gases are heated up, the molecules are bouncing around, they have more kinetic energy, and thus they collide and they are bouncing and they have that elasticity and they are not able to be dissolved. So thus, whenever you increase your temperature, you will decrease the solubility of a gas with a liquid. All right, then for 25, I want to remind you guys very lovingly, there are formulas on the back of your periodic table. Right there, big M, molarity equals the moles divided by the liters. So that's the moles of the solute divided by the liters of a solution. It is on your periodic table. On the back of it, you guys are given this for every test, every quiz, everything. So please don't tell me you don't know the formula when it's given. So in this case, for number 25, you have molarity of a solution that contains 0.769 moles of sodium chloride in 2 liters of water. So there is my moles of my solute. There are my volume, my liters already for water, which is my solution. So I'm trying to find molarity, which is just big M equals moles over liters. So you take 0.769, divide by 2, and you end with 0.385 molarity. Then for 26, M1 V1 equals M2 V2. So we are given, you have 10 molarity of stock solution of sodium chloride. And then you want to discover how much stock solution would you need if you wanted to make 2 liters of 6 molarity solution for a lab. So M1 V1, M2 V2. 10 molarity is your M1. 6 molarity is your M2. That's what you're wanting to find. And then 2 liters is your V2. So when you set it up with your M1 V1 equals M2 V2, 10 times V1 equals 6 times 2, which ends up being where you have to take 12 divided by 10. I know I missed that step. I was getting excited. So your V1 will equals 1.2 liters. All right. Acids and bases, Unit 4. The ones that I have here for the properties that I really want to stick out, that acids are sour, they feel slippery, they turn litmus paper red. So red litmus paper would stay red, blue litmus paper turns red, acid. Please remember that 0 to technically 6.9 is going to be your acids. So anything when it says below 7 is going to be an acid, and then above 7 is going to be a base. So remember that absolute 7 is your neutral. Then for bases, they're bitter. They turn litmus paper blue. So thus, blue litmus paper stays blue. Red litmus paper turns blue. They feel slippery. Remember that we played with baking soda and baking powder in class with water. We mixed the two, and one felt sticky, one felt slippery. Baking soda felt slippery. Baking powder feels sticky. That's because one's an acid, one's a base. Please keep that in mind. All right, so strong acids, strong bases. What is happening is ionization. So you have your molecules here, like hydrochloric acid. And if he gets in water, what happens with that hydrochloric acid is they break apart. And you have a positive and negative parts running around. So you have all of that dissociation, that disconnection, and all of it is like every single hydrochloric molecule now is broken and dissociated. So you have all those extra positive and negative ions. So because of that, when you stick two electrical currents into that solution, and it is able to have a clear and smooth jump from positive, negative, all the way through the solution to get to the other side, and thus turning the light bulb on brightly. That is because of the complete ionization with those molecules. Then, for weak acids, weak bases, the light bulb shines dimly. So that is because they don't fully ionize. Some of them stay together, some of them break up, and it's only a partial ionization, separation, dissociation, only partial. So there's not many for them to basically, and I did this in class as an example, leapfrog to and be able to have that current, the electrical current, go through the water to turn that light bulb on brightly. The current's still there, but the thing is, it's not being able to get to where it needs to because there's not enough positive and negative ions. So for 29, it's going to be an acid. 30 is going to be a base. 31 is a base. Remember that when you increase, when it is greater than 7, it is a base. When it is less than 7, it's an acid. 32, drain cleaner, is a base. 33, when litmus paper turns red, is an acid. Less than 7, acid. Water is neutral, that's your pH of 7. Litmus paper turns blue, that's a base. Hydrochloric, the fact that he has H in front, and this is just really basic chemistry. If there's an H in front, like that, is going to be an acid. This isn't always the 100% of the time, but right now at this level of chemistry, hydrochloric, seeing the hydrogen in front, it's going to be an acid. All right. Here we go. So you are going to have 2 of these on your final, and I would really encourage you guys to try to remember a few things. First off, your reactants are either the acid or the base, not your products. Acid or bases are going to be defined with your reactants. So the easiest way to remember this is who gave up the hydrogen. So when I look at NH4 and OH and I compare him to the products, I see that NH4 becomes NH3. There's a hydrogen missing between the two. So NH4 becomes NH3. So because he gave up that hydrogen, he gave it up, he is the acid. So NH4 is the acid. Now, OH is going to be the base because he gained that hydrogen. The base is the one that gains it. So OH ends up gaining it and forming H2O. Then, how you identify conjugate acids and conjugate bases. Your conjugates are only your products. They are only on the product side. So NH4, the subspecies, what he becomes when he gives up that hydrogen, what he becomes is going to be NH3. So NH3 is a conjugate base. And I know that sounds weird, like, wait, Misty, he just was an acid. Yes, I know. That's why he has a conjugate base. Then OH becomes H2O. So his pair, his match, is a conjugate acid. The reason for this is, think of it this way. If you went the reverse and you're going from products to reactants, H2O ends up technically giving the hydrogen back to form the NH4. So because of that, he's the conjugate acid. Because if you did the reverse from products to reactants, he becomes, gives up the hydrogen, forms OH, and NH4 takes on that hydrogen. So that is why their mix match. An acid is always paired with a conjugate base. A base is always paired with a conjugate acid. They have that opposite conjugates. Now, for 39, NHSO4, it will be your acid because he gives up his hydrogen. H2O, I get it, it's water. But remember, water is amphoteric. So meaning in a equation like this, he can function either as an acid or base. So H2O receives that hydrogen. So he's the base. He forms H3O. So that is his conjugate acid. Then SO4 is what was formed from our acid. So he is the conjugate base. All right. Remember with naming, I have my clipboard. So remember with naming on this part. When you see more than two elements with like hydrogen, so we have hydrogen 2, SO3. Remember that in my classes, you have to look at your polyatomics. So H2SO3 is what you have. So look at the back of your periodic table. For SO3. So when I look there for my SO3 on my polyatomics on the back of my periodic table, I get SO3 sulfite. I get the polyatomic sulfite. And because this is related with sulfur, just like sulfur or phosphorus, I cross out the ITE. And I form sulfurous acid. Now, all I did was add an OUS. Remember that with phosphorus and sulfur, you have to add the UR back. So all you do is change the ITE to an OUS. Now, ITE becomes OUS, but ATE becomes IC. Those are ternary acids. I call them polyatomic acids. in my class because it helps you guys remember to look at the polyatomics on the back of the periodic table. So remember that anytime you have an ATE, he ends with IC. And when you have an ITE, it ends with OUS. And with sulfur and phosphorus are the only two that you have to add the URs back to make it phosphorus acid. Now, remember that only binary acids have hydro in front. So in this case, for 41, you have hydrosulfuric acid. So because hydro is in front right there, that automatically tells me, okay, all I have is two things, hydrogen, sulfur, that's it. If it was hydrobromic, hydrochloric, those are only related to hydrogen, bromine, hydrogen, chlorine. That is it. Anytime you have that hydro in front, that is telling you automatically, hey, there's only two elements involved, hydrogen and the other element. So, hydrosulfuric acid. And my H2S is going to be the correct chemical name formation because remember that sulfur has a -2 ionic charge and hydrogen has a +1. So I need two hydrogens to make up that negative charge for sulfur. Remember, they have to be neutral. All right, here we go. Almost done, guys. Thermochemistry, yay. So the first definition is calories. So keep in mind that calories are when you have, for water, 1 gram of water of 1 degree Celsius. Then specific heat is going to be for a substance. So again, that's the amount of heat needed to rise the temperature of 1 gram of that substance by 1 degree Celsius. So, 46. Again, I don't want anyone to tell me they don't know this formula on Monday, Tuesday, or Wednesday when it is on the back of your periodic table. Please remember that Q equals MC delta T, and delta T is going to be your final temperature minus your initial temperature. So we're trying to find heat in the first problem, and that is for Q. They gave us a mass of 34.4 grams. They gave us the specific heat of 2.44 joules divided by the grams of degrees Celsius. Then they gave us the starting temperature of 25 and an end temperature of 78.8. So final minus initial, 78.8 minus 25 gives me 53.8 degrees Celsius. So all I do is plug it up. So Q equals 34.4 times 2.44 times 53.8. So I end with 4,515.8 joules. Now, 47, I messed up on the answer. So I'm going to have to tell you guys the correct answer. All right. So again, we start with the formula of Q equals MC delta T, but we're trying to find just specific heat, which is C. So that's going to form into C equals Q divided by M delta T. So Q started off with 5,696. Then, where'd my marker go? Then I'm going to have a mass of 155. So then I have a final temperature of 40 minus the initial of 25, which is 15. So when I take 56.96 over 155 divided by 15, you should get this answer. You should get that answer. Ignore the answer I have on my screen. But when you have 5,696 divide by 155 times 15, you should get 2.45 joules divided by grams of degrees Celsius. That is the correct specific heat for that. So, all right. Whew, I'm getting out of breath. Been talking for almost an hour now. All right. 48. What they're asking is literally, what's the potential energies? So guys, remember, straight line, potential energy. That is going to be your phase changes. Please remember that you cannot have kinetic energy and potential energy happening at the same time. You cannot stay still and move at the same time. Right now, I'm having a lot of kinetic energy. If I was to just stop, I would have potential energy. So when they're asking for the letters represented for the stored bonds, they're just literally asking you for potential energy, which is going to be D and B, your phase changes. Then for 49, they're asking you, which ones have the kinetic energy? And that is going to be your phases, just your phases. So those are your curves, your lines going like this. So that's going to be E, C, and A. E, C, and A. All right, so 50. Which letters represent a solid, liquid, a gas? So again, your phases are going to be the going up lines. So E is going to be the coldest. You're starting at a negative 50 degrees Celsius, which to me is pretty cold. Don't know about you guys, but I would be freezing. So remember that, put this in a water sense. Ice, solid. Water, liquid. Gas, steam. So solids would be E, liquids would be C, gases would be A. Then for 51, and I'm going to try to get this to be bigger real fast. So for 51, they're talking about representing for vaporization. So remember that vaporization is a directional phase change. So yes, it represents letter B, but it's 4 to 5 B. Then for condensation, that's going to be from B as well, but it's going to be 5 to 4. Remember that vaporization, there we go. Vaporization, you're going to get warmer. Like you're literally going from a liquid to a gas. So you're still getting warmer. So if you're getting warmer, you're going to be taking in heat. So you're going to have this endothermic reaction happening when you get warmer. But when you're condensating, so that means it's getting colder, it's coming together, it's getting calmer, your gas molecules, and you're forming, perfect example on my awesome smoothie, condensation is forming on my smoothie. So the water molecules around are coming close to there, and they're coming together and forming a water molecule. So it's getting colder. It's getting colder. The air, that steam is getting colder. So thus, if it's getting colder, heat is leaving it. That would be exothermic. So then, which letter represents fusion? So fusion is any time when you're going from a solid to a liquid. This is also called melting. So anytime, don't know why there's so many awesome words for the same things. So that's going to represent D, but that's 2 to 3 in directional. And you're getting warmer, so that's going to be endothermic reaction with fusion, where freezing is going to be exothermic reaction. It's releasing heat and getting colder. So in the solid change to a liquid, so when we're going from a solid to a liquid, so we're having fusion, we're going to be an endothermic reaction because it's getting warmer. When I am going from a solid to a liquid, I'm getting warmer. Where when I'm going from a solid to liquid to a solid, I'm getting colder. So that would be exo. Whenever I'm going from gas, liquid, solid. When you freeze water, exothermic reaction. Endothermic, when you take in the heat. All right. Then here is energy diagram. So thus, Please remember that B, from your reactants to your activation complex, the difference of that, the energy, is going to be your activation energy, the energy needed to cause the reaction to occur. How much energy you need to climb up this mountain right here. Then for A, those are your reactants. D is your products. C is going to be your activated complex. B again is your activation energy, the energy needed for the reaction to occur. So please remember, when your products are higher than your reactants, so D is higher than A, that is endothermic. Now, if D happened to be lower than A, that would be an exothermic reaction. So anytime your products are higher, that's endo. Anytime your products are lower, that's exothermic. All right, unit 16, unit 6. Whew, thank goodness it's not 16. All right, nature of the reaction, depending on who they are on the periodic table, will define on who they react with. Example, noble gases don't like to play with anyone because they have a full valence electron of 8. So thus, they don't play well with others. But group 17, who has a -1 ionic charge, they love to react with other people, other elements. And group 1, who has a +1 ionic charge, they love to react with others. So they actually, group 1 and group 17, love to bond together. Then, concentration. So we're talking about reaction rate. So if I increase the concentration, and the best way I can do to describe this is dodgeball. When you start playing dodgeball, and you have a bunch of people together and there's just like balls flying everywhere and you're trying to dodge them, a lot of people get out very, very quickly. That's because the concentration of the kids on one side and the kids on the other are a lot. But as the reactions occur, they get a smaller quantity of people. Towards the end of a game of dodgeball, you only have like a couple kids. And I don't know about you guys, but whenever I played dodgeball in elementary school, when it just came down to like one person on each side, I would just be like, oh my gosh, just get them out. Like I would hate it because it would take forever. So remember, if you increase concentration, you increase the reaction rate. All right, surface area. If you increase surface area, you increase the reaction rate. When you decrease the surface area, make it more condensed, making a smaller surface area, not smaller surface area, but less of the surface area. Like example, powdered sugar. Because it's ground up, the powdered sugar has a high number of surface area. All the molecules are exposed. They're able to be absorbed very, very quickly. But if I had a cube of sugar, it doesn't have a lot of surface area. You have to smash up the rest of the cube to be able to expose those molecules inside for them to bond and to have that reaction. So thus, when you increase surface area, you increase your reaction rate. Again, when you increase temperature for most things, you will increase the reaction rate. Sugar will dissolve very, very quickly in a hot coffee. But will not dissolve very quickly in my cold smoothie. All right. Now, a catalyst. A catalyst is there to help the reaction occur. It does not become a part of the reaction. It does not bond with anything. It is just there to help speed it up. And how it helps speed it up, just like matchmakers, they cause the activation energy, this B right here, this activation energy, to decrease. So my hill, my mountaintop, just decreased. So thus, the reaction was able to occur and go over it quicker. So thus, when I add a catalyst, I decrease my activation energy and thus increasing my reaction rate. All right, for 61, reaction rates. Guys, think of it this way. This always cracks me up. If I rode a bike to school, it'd probably take me a solid hour to get to school. I'll be real, like a solid hour. But if I drove my car to school, it takes me about 15 minutes. So think about it. Which one went faster, the car or the bike? And I'm hoping you're thinking car. So thus, if I increase my reaction rate, increase the speed that this is happening, I will decrease the time it took me to get there. They don't go together. My reaction rate doesn't make it go faster, thus more time. No. Think of it in the sense of a car and a bike, that if I increase my reaction rate, if I got to school in my car in a faster reaction, a faster speed, thus that would decrease my time that would take me to travel there. So what would happen to the reaction rate? It increase. What would happen to the time? Decrease. All right. Le Chatelier's principle is just a definition that states that a system at equilibrium will shift the equilibrium point in order to reduce the stress. All right, equilibrium, a forward and reverse reaction at the same rate. These are both definitions that you need to know. So in number 64, in my classes at least, we use this as an example of a seesaw. Pretend this entire reaction, this entire equation right here is a seesaw. And this is the point of your seesaw. So right now your seesaw is dead even, straight across. You have your reactants and you got your products. And they're dead even. And they can go either way. They can go left or right. So identify, where is heat? He is on the product side. So if you added another child of heat, or I removed it, sorry, it says remove heat. If I remove the child of heat off my seesaw, and right now it's dead even, and I took a kid off of the seesaw, that means that side that removed that would go up, and that would be the right shift. Then they want to add water. So water, if we're back at even, is on the right side. It is a product. So if we added another kid onto the seesaw, right now we're like perfectly even. And what would happen would be it would go down, causing a left shift. And I'm trying to draw this so it's a little better. So think of a seesaw like this. And I know this is kind of silly, but it does, once you understand the concept of it, removing a child on and off a seesaw, it makes it a lot easier. So in this case, let's do adding water. We added water, which was on this side. So if I added another water to an already even seesaw, that means this side goes down, causing this to go up, which this is the left and right side. So because the left side is up, it's going to be a left shift. Then, whenever I removed nitrogen, so because he's diatomic, he has to be 2, so when I removed him, that right side would go up. When I added NO2, that side, left side would go down, right side would go up. When I removed H2O, so I removed a kid off the right side, when I removed him, he would go up, causing a right shift. When I added N2 is on a product side, so thus when I added more, that would make his side go down, causing the left shift to go up. Now, pressure is unique. Pressure, you just have to memorize. When you're adding and taking away something, it's pretty easy to know your shifts, like, oh, it's a right shift, left shift, whatever it is. But pressure, it's all about the numbers of your moles. So in this case, please remember that gases are the only ones that take into effect for Le Chatelier's principle. So you have moles. Moles are the only ones that take in consideration of gases. So you have 2 moles of N2H4 gas. You have 2 moles of NO2, so that's 4. So nitrogen is 3, water is 4, that's 7. Both of those are gases. None of them says solids, none of them says liquid, so thus you count all your moles. It's a 4 to 7. So whenever you increase pressure, whenever you increase that pressure and causing the volume to get smaller, it will shift towards the higher number. So which number is higher, 4 or 7? 7 is higher. So because it increased the pressure, that would cause 7 to rise. So thus, it's going to be a right shift. Now, if I decrease the pressure, it's going to shift towards the smaller number. So, which one's higher, 4 or 7? The left side, 4. So it's going to be a left shift. Please let me know if you guys need more help with that. I know that doing the whole left side, right side shift thing can be confusing, but try to put it in a sense of a seesaw with children on them and taking the kid on and off, what side would go up. I know when I was a kid, I used to play at the park with my sister, and I would purposely jump off one side to watch her fall. So I'm sure a lot of you have played on seesaws and have watched other children fall when you get off of it, so I know you understand that example. All right. Our last unit, yay, unit 7. All right. So, gas laws. Remember Boyle's, Charles, Gay-Lussac. So Boyle's is P1 V1 equals P2 V2. Then Charles is V1 over T1 equals V2 over T2. Gay-Lussac is P1 over T1 equals P2 over T2. Please remember Boyle's, this guy right here, has a straight P1 V1 equals P2 V2. Thus, he has a inverse relationship. Meaning, if pressure goes up, volume goes down. It's inverse. While Charles and Gay-Lussac both have direct relationships. So meaning if volume goes up, temperature goes up. If pressure goes down, temperature goes down. They are directly related. In my class, we did the examples of bad breakups, good relationships. Remember that Boyle's would be a bad breakup. You would never want to be near your ex. Just think about that. Then Charles and Gay-Lussac, those are good relationships. You would want to be with the person that you are dating or seeing. So thus, if they go there, you go there. If he goes here, I go there. That kind of example. All right. So for 65, that would be volume. 66 is increase. 67 is decrease. All right. 68 is talking about an example. Basically, if I went to the grocery store and I bought balloons inside, and it was really cold in the grocery store, and I took my balloons to a party outside, and it was really, really warm. What happens to the balloons if the pressure is held constant? Well, the balloon's volume will increase because the temperature increased. Please remember that relates back to Charles. Volume increase, temperature would increase. Temperature increase, volume increase. All right, 69. We are almost done. All right, so on your final, you're going to see one of each of these equations on how to do those mathematically. So the first one we're talking about Charles. So it's V1 over T1 equals V2 over T2. So identify 90 milliliters is my V1. My T1 is 57 degrees Celsius, but remember, you have to add 273 to it to get it into Kelvin. All gas laws have to be in Kelvin. Then volume 2 is my unknown. And then my T2 is 132 plus the 273. So when I set this up, you're going to set up 900 divide by 330, equaling V2 over 405. Now, how I did this in my class is the crisscross, the Chinese star, whatever you guys said it was called in your math class, where I took 900 times 405, giving me 364,500 equals to V2 330. Then you take the 330 and divide it, take 364,500, divide by the 330, giving you V2 as 1,104.5 milliliters. Whew, a lot of talking on that one. All right, 70. 70 is boils. So remember that is a inverse relationship. So if my P1 goes up, my V1 goes down. So they're inversely related. So, 2.7 liters is my V1. My P1 is going to be 1 atmosphere. They tell you a temperature, but it doesn't matter because it's held constant. It doesn't change. Then it tells you that the pressure changed to 0.9 atmosphere. What would be the new volume? So I take 2.7 times 1 equals 0.9 V2. And I take my 2.7, divide by my 0.9, and that will give me 3 liters. All right, 71. 71, P1 over T1 equals P2 over T2. So if my atmospheres, again, my first atmosphere pressure that is mentioned is 12 atmospheres. My second pressure that's mentioned is a 16 atmosphere. So that's my P2. And I know this sounds silly, but underlining and identifying it on the test really does help, guys. All right, then my temperature 1 is 25 degrees Celsius. Remember to add 273. You have to add him in there, so he becomes 298. But I don't know my final temperature. So I set it up, 12 over 298 equals 16 divided by T2. So I get 4,768 equals 12, divide him by 12, and I get 397.3 Kelvin. So please keep that in mind. All right, last 2 problems, guys. So keep in mind that gas is unique, that every single gas in the whole wide world, 1 mole of him will equal 22.4 liters, period. Where when we're talking about substances like H2O, as water, he's going to have his own grams from the AMUs. But in this case, our liters, you just have 1 mole of that substance equals 22.4 liters. So I start with 6.2 liters, divide him by 22.4 liters to get the moles, and I have 0.28 moles of that. Then the volume will be 88.92 grams of O2. So I get my grams to moles, moles to liters. So thus, even though it is grams to moles, the liters is going to be constant. It's still 1 mole to 22.4 liters, ending you with 62.2 liters of O2. Okay, so that wraps up the whole study guide. Please message me if you guys have any questions or need me to reiterate or talk about another section. Remember that there are a grams to moles, grams to grams problems already made on the YouTube site, so just look those up. Also, balancing equations. There's also study guide reviews already made, YouTube videos for Unit 1 and Unit 2, which are your hardest units so far that I have seen you guys try to do, which is your moles and stoichiometry. Please remember we have a wacky final schedule. It's going to be third period, darkness from the board, sorry guys. Third period and fourth period are going to be on Monday. And remember that I have the kids that are in fifth period who have a fourth period lunch. You come during fourth period. Then on Tuesday, that's going to be sixth and seventh period. And then Wednesday is going to be first and second. Those are the schedules. So those are posted on eClass, and there's more videos already made on eClass under the content for second semester video support help. I hope you guys have a great weekend and that you are studying hard. All right, bye.